Hi, welcome to the video lecture on simulation of solid state drives. In this video, we are going to see how to simulate the closed loop control of permanent magnet synchronous motor drive using MATLAB Simulink. The general block diagram of the uh, closed loop control of permanent magnet synchronous motor is given here. We have a three-phase inverter which is feeding the permanent magnet synchronous motor. This three-phase inverter is being controlled by a space vector pulse width modulation. The three-phase current of the machine has been taken and the three-phase RYB current along with the rotor angle is reconstructed into alpha and beta frame. This alpha and beta frame is again reconstructed into DQ frames, and DQ are the direct and quadrature axis. Quadrature axis is responsible for the torque. So we have a speed which is also sensed, and the speed is compared with the reference speed, and it is given to you, that error is given to a PI controller, which in turn is fed into another PI controller for Q axis and another PI controller for D axis, and again this DQ is converted into alpha beta and it is given to SVPWM module to generate the PWM signals for this three-phase inverter. This block diagram is what we are trying to construct by using the MATLAB Simulink. So let us go into the simulation. Let me try to open a new Simulink model, create a new Simulink model, and let me go to the library browser. In the library browser, I go to Simscape, Electrical, Specialized Power Systems. Under Specialized Power Systems, let me take this Power GUI because this is essential for simulation. Double click on this. Let me change that to discrete mode, and the sample time let it be 5 e power minus 6. Click apply and give OK. The same time, I go to debug and keep my simulation diagnostic settings as uh, solver. Go to solver. I simulate for a time of 1.3 seconds and go to the solver. Try to take ODE 23 T and maximum step price is 1 e power minus 5. So these initial settings are needed to do the simulation. Let me give OK. Now again I go to library browser. Under library browser, under Simscape Specialized Power Systems, I have uh, electrical machines. Under electrical machines, I have permanent magnet synchronous machine. I drag it on, put it on the screen. So this is the machine which I'm trying to simulate. So let me double click on this, and it is a back EMF waveform is sinusoidal, rotor type is round rotor, mechanical input is torque, and preset model, let me take 6 Newton meter, 300 volt, 4500 RPM, the fourth preset model which is already available, and the parameters of all that is given here. I have a J, moment of inertia, frictional coefficients, number of poles of the machine, which is also important for calculating doing the control techniques. And let me go to advanced mode. In this advanced mode, discrete solver model, you keep it as backward Euler robust and click apply and go OK. Now this has to be given fed from a PWM inverter, that is three-phase inverter, for which again I can go to power electronics. Under power electronics, you have a universal bridge, which is something like here, universal bridge. Drag it and put it here. Let me try to swap this because I'm going to feed a DC input, get an AC output from this and feed it to a motor. So I format it, flip the block from left to right so that this plus and minus will come on the left hand side and the ABC will be on the right hand side. Similarly, I have in the sensors and measurement, I have three-phase measurement. You can just, three-phase VI measurement. We just drag this drop, double click, and you change that to face, click apply and give OK. And I'm going to connect these two blocks like something like this. So let me have a connection between all these three. And similarly from this A, I connected to the motor A, B and C. So I connected everything. And this is a simple measurement to measure what is the current and voltage which is given taken by the motor and fed into the motor. Now I have a DC power supply is needed to feed this. So double click those in the universal bridge and you remove this, replace this thyristor with IGBT with diodes. Click apply and give OK. And I have sources. I need sources. Sources, you go to sources. In the sources, you have a DC voltage source. Drag it, put it on the screen and connect it here and change that DC voltage source to a voltage of 350 volts. And I need a constant for this torque. So go to SIMULINK. You are commonly used to have a constant block. Put it here, and this constant is let me fix it to 5 because maximum Newton is 6 Newton meter. So I can give 5 Newton meter. That is not an issue. Then I select this bus selector block and connect it here. Double click on this. I need stator A, stator B and stator C. All the three I will select. Then I need rotor speed, rotor angle and electromagnetic torque. Again, all these three also I will select. Sorry, I want to select. Let me select one by one. Add B, C and rotor speed. Let me add this and this. I remove these two and click OK. So now I have 6 uh, terminals here, which is stator current A, B, C, rotor speed, rotor angle and electromagnetic torque. So let me connect a scope for all to view all this. So let me go to sinks. You have a scope. Take the scope and double click on the scope. You go to settings. You have 6 ports and I need, let me put it in 2x3 mode or 3x2 mode, whatever you like. 3x2 will be much better. 3x2, yes, okay. And let me drag this comfortably to put it on the screen. Let me drag this. I will connect everything. Everything is connected now. You can just look into this. Yeah, this is how the simulation will look like. So let me have this very closer so that I can use the remaining spaces for developing the control circuit. And this is one uh, part has been completed till now. Now let me mux all these 3 currents into a single mux value. So let me go to commonly used. I have a mux. So I put a mux here and I connect. I double click on this, change the number of inputs to 3 and connect all the 3 inputs here, that is stator current A phase, B phase and C phase. And I have a block called go to, which is a label. So I have a signal routing. In signal routing, I have a go to block. Use this, and I need a from also. So let me take these 2 blocks, go to block, and I connect. I reduce the size of this so that it looks good. Double click on this A. I give a name like I have a current. I am measuring the current of all the 3 phases. So IABC. I give IABC, click apply and give OK. So now this label can be labeled here so that the signal, you can just click this, you have IABC here, which means that whatever it is coming here will be again taken from this point. I don't need to connect this point and this point. It has been, this is from and go to how we can use it in simulation. Now I need, this is actually rotor speed and this is actually theta. rotor speed, I want to look it in radians. It is available in radians per second. I want to convert that into RPM. So for which I go to a block called gain, which is already known to us. Let me take a gain block and connect this speed here, and this is 30 by pi. 30 by pi. So which is a constant which is used to convert this omega into omega in radians per second into RPM. Similarly, this rotor angle theta has to be multiplied with the number of poles. So let me take another thing and I connect this rotor angle theta. Number of poles is 4 in this particular machine. You can just go to the machine and look at the in the configuration parameters. You have number of poles as 4. So if I multiply this number of poles with 4, that becomes omega t. Now I take 2 more blocks like this. So this is for speed in RPM. So I put it as capital N, and this is supposed to be omega t. So I connect it and put WT. So this is omega t. So now I have speed as well as omega t here. Now I copy all this and have all the 3 signals. IABC is one, speed is the other one, and omega t is the third one. So let me take all these 3 and keep it here. Now let me go to the block diagram again. So the speed has to be compared with the actual speed. Reference speed and actual speed has to be compared, and it has to be given to a PI controller. So let us complete this. So this is the reference speed, actual speed, and I have to compare it with the reference speed, for which I need a summer block. Summer block is already available in commonly used points. Double click, change this sign to minus, and sorry, this is supposed to be the reference speed. Let me delete this. This is supposed to be the actual speed. Reference speed is supposed to be in constant. So let me give it as some 2500 RPM. So let the machine run at 2500 RPM. Let me give it. And this has to be given to a PI controller. This reference actual speed, and this is actual speed, this is reference speed. The error between these two is given to a PI controller. So let me take a PI controller. PI controller is available in continuous. You can just have a PID controller, drag it and put it on the screen and connect it, and double click on this and change this to PI, and we will give the values later. So let me give apply and give OK. So now this is the this point has been completed. Now let us come here. I have all the 3 currents which is measured at this point, and I want to convert this measured current into alpha beta. So ABC to alpha beta is required. So for which again you go to library browser under Simscape, specialized power systems. You have uh, uh, I think it is available in control. Yeah, you have ABC. I need ABC to alpha beta. So I have ABC to alpha beta. You can see here ABC to alpha beta 0. So let me drag it and put it here. All the 3 currents are available here. So it is ABC is available, and this is being converted into alpha beta. So this alpha beta, if you look at alpha beta, has to be given to another conversion called DQ, for which this uh, uh, omega theta E is required. So let me try to go here. So I need alpha beta to DQ. Again, I go here. I have alpha beta to DQ. Yeah, it is available here. Alpha beta 0 to DQ 0. So let me drag it and put it over the screen. Yes, now this is alpha beta is given, and I need a omega t for it. So I connect the omega t also here. So now I have 2 divisions. One is IABC and this omega t, which is required for converting the current from ABC to DQ, and this is what it is given here. Now I have DQ component. D has to be given to a PI controller. Q has to be have another summer which is out of this speed PI controller. So I take another summer, I put it here, and this is having two components, D and Q. So let me put it somewhere here so that it becomes easy for us to, I need to demux. So I go for Simulink library browser. I have a continuously, this is demux, and this DQ0, all the three are available here. So I split this into 3, and little bit elaborate this. I have, is good, it looks good. Now this first one is D, second one is Q, and third one is 0. So 0 is not needed. So let me have some sort of a terminator which is available in the continuously commonly used, and I will terminate this Q 0. Okay, now the first one is D, second one is Q. So again, let me go show the block diagram. D is compared with another signal which is generally a 0. Q is compared with the output of the PI controller of speed. So the second one is this one. So let me take the second one, keep it here. And first one, I had to compare this with a constant, and that constant is supposed to be 0. This is the constant. This constant is supposed to be 0. So this is actually a D component, and this is actually Q component. Let me little bit drag and put it down so that this has to go up actually, and this has to come here. So it is something like this. Yes, now this is actually D and Q, and this is D and this is Q. Okay. Now this DQ has come here, and this DQ has to be given to two different PI controllers. So let me take a PI controller here, put it, and let me take another PI controller here, put it. And these two both are given here. Then now let me take the SPWM DQ to alpha beta again. So I need a DQ to alpha beta. Again I go here. I need DQ2 alpha beta, which is available in controls DQ2 alpha beta. So look at this, DQ2 alpha beta. Yeah, it is available here, DQ2 alpha beta. Let me put it here. So I need DQ0. All the three has to be given. So again, I need a mux for it. So let me bring it closer so that I can put little bit components on the other side. It will be comfortable for me to visualize everything. So I need a mux. So again, go here, go for mux, which is available in commonly used mux, and this is supposed to be a 3 signal, because Q0 is generally a 0. So this is actually D, and this is actually Q, and I need one more which is supposed to be 0. So let me put this little bit comfortably. Let me put it comfortably here. Yes, everything is good. Now I need a constant which is supposed to be 0 here. I put a 0, and this is supposed to be dq, and I need a omega t which can be taken from this point, omega t. This is omega t. Yes. Now this I have alpha beta 0, which I need to convert back. If you look at the block diagram, I have dq which has to convert into alpha beta. So uh, I have dq2 alpha beta, dq2 alpha beta, which is given to two PI controllers. One second. Now this alpha beta has to be given to SVPWM module. So I need a dmax to separate this. So I take a dmax. Now this is alpha beta and this is supposed to be 0. So I terminate it. And I need a SVPWM module, which is again available in the library browser under Simscape. You can just go to Power Electronics control. In Power Electronics control, it is not available, I hope. Yeah, Power Electronics control. In Power Electronics control, you have SVPWM generator 2 level. Just take it, SVPWM generator 2 level, and I have to give it to this SVPWM generator. The SVPWM generator, you change the magnitude to alpha beta components, and switching frequency you give it as 5000. Click apply and give OK and connect this alpha beta, and I have I take another pulse which is supposed to be, I type it as pulses, 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 and this pulses is what I'm supposed to give it here to the gate signal. So I connect it like this. I can rotate it comfortably so that I can select these pulses, and this pulses is available for switching the inverter. And this is how the entire simulation is. Now let me give the PI controller values. This is speed PI controller. I double click. Speed PI controller is supposed to be 0.0059, and this is supposed to be 0.0946. This is speed PI controller, and this ID PI controller is 0.1723 and 2.73. This IDPI controller and the IQPI controller both are same, so I just copy it and put it here. Both are same. Values are same. So I just copy and put it here. And this is what all about the uh, creating the Simulink diagram. So let me put a scope to view the speed at this point n. So let me have a scope here, which is again taken from Simulink Sings scope. Let me drag it and put it on the screen. And this is what I'm interested to look. So let me put a scope here. And now let me run the simulation. And let us wait for the simulation to run. And I could able to see the results of the simulation here in the scope. My actual speed is require the machine to run at 2500 RPM. You could able to see that the machine speed is almost settled at 2500 RPM. So this is how the closed loop simulation is going to work on the machine. So now this is running here. Almost it is maintaining a speed of 2500 RPM. So let me stop and let me have all this in a single file so that it looks easy for us.
ಮಣಿಂತೆಗಳು ನನ್ನ ಆತು ಕಲಿಯೇ ಇನ್ನು ದಣಿ ಅಂದ್ರೆ ಹದಿನೇ ಬಂದನು
Okay, let me have this separately. This one is one input and this is another input. This is another input and this is another input. I can connect this two because these both are omega t. This is omega t and this is also omega t. So I can delete this and connect this directly here. Okay, now this is okay, good. Now let me select all this, create a subsystem from this. One second, control is set. Let me select all this up to here, create a subsystem. Good, it looks good. Now I reduce the size of all this. This is actual speed. This is speed in RPM. This is the current IABC and this is the angle and this is supposed to be the pulses for the inverter. So let me have all these points here and put it somewhere here so that my simulation will be looking in the maximized size. I can still reduce this size, keep it somewhere here for better understanding of the controller. Yes, it looks good. Now what I try to do, I put a step input instead of this 2500. I go to commonly used. I have not in the commonly used. I have maybe in the sources. I have a step signal. Yeah, this is the step. I put a step. And initially, step time is supposed to be, say, for example, 0.65 or 0.8, for example. Initial value is 2500 and final step time is 3000. Final value is 3000. Similarly, I give a step change in the load also. So let me delete that load, put this step time, and the step time here is supposed to be 0.45. Initially, let it be 5 and finally let it be 3. So now let me run the simulation and observe what is happening at the speed. Now the simulation is started running. We have given step change in the load at 0.45. So naturally at 0.45 there should be an increase in speed because I'm decreasing the load. Then again it has to come back. Let us see what is happening at 0.45. There is an increase in speed and it has to come back again at 2500. At 0.8 I'm increasing the speed from 2500 to 3000. So now again it has come back to 2500 and at this point I increased the speed, sets reference speed itself. Now it is moving to 3000. So very exactly my motor is tracking the speed. Motor is tracking my reference. So this is what all about the closed loop control of permanent magnet synchronous motor drive fit from a inverter which is controlled by SVPWM technique. Thank you for your patient listening. Thank you.